Yeah, hello everyone. Good morning all. This is Dr. Abdul Pasha. So, course is Power System Operation and Control. Here today's topic is about series compensation strategy. So, basically we use this method in a power system network to compensate for any unbalances in voltages or currents case, and we can overcome the mismatch of the power system components which are lagging behind the supply voltage, and it can ready to compensate for unbalances in the system. So coming to series compensation, what are the main objectives of series compensation? So here the effect of series compensation is based on the some factors considerations. So what are the basic factors means they should be determining attainability. So how can they will be treat means maximal power transmission. Maximal power transmission is going to be treated. Steady state power transmission, limit and transient stability case, voltage stability case, and finally power oscillation damping case. So these are the main key features about effect of series compensation strategy, that is based on the these factors means which will influence mostly on the system parameters. So here maximal power transmission means when we achieve maximum power means, for example, this is the power generating station. From this power generating station to reach to the power to the load end, we are going to connect the transmission network or transmission line. So this transmission network or transmission line is going to be transmit the power to the load with a suitable parameters case. That means maximum power is going to be transmitted through a specific case. So under steady state power transmission case, this can be achieved with only maximum power limits. So the limits which are applicable when there is a 10% extra increase in power is going to be sent to the load. This excessive power is going to be treated as a loss coefficient, and this will be neutralized in such a manner. So here to minimize this loss coefficient, we are going to send extra more power. This will be treated under steady state power transmission case. So to achieve steady state power transmission, we need to compensate with some more extra power capability. This can suppose to compensate the line of the particular loss case. Limits transient stabilities are going to be considered. Limits means the power system capability is going to be considered. Suitable limits means they are going to be applicable with two parameters, alpha and beta. So these limiting coefficients will make the system to be happening under transient stability case. So when these limits are within the permissible case, then only we can suppose to achieve transient stability of the system. And coming to voltage stability, the voltage stability can be provided suitably by providing compensation through the capacitors and through the line compensation strategies, all these cumulatively together to form the voltage stability of the system. So this will balances the system conditions. Wherever the lag of response in the line, that can be compensated by this, making voltage stability consideration. Power oscillation damping also provided, means due to the presence of the harmonics in the system, the unbalances in the system cases may lags this response. So this may be the reason due to the ripple coefficients present in the line. So that may be treated as one of the power oscillations. So these damping levels can be supposed to be compensated to the suitable extent by providing suitable control strategy methods which will be introduced into the whole power system network. What is the concept of series capacitive compensation? This is a suitable method, and here the basic idea behind this providing series capacitive compensation is to decrease the overall effective series transmission impedance. That should be from sending end to the receiving end. So that is X in the line is going to be treated, that is the reactance coefficient. X is the reactance coefficient. That is P equals to V by 2x. P equals to V by 2x sine delta. So this mostly considered as one of the coefficient that should be relationship characterizing the power transmission over a single area. This makes the system over the concept of series capacitive compensation, which is ready to give or boost up the voltage levels wherever the system lag of response. Let's we suppose to see that considering a simple two machine model with a series capacitor compensation line, whichever for the convenience case, it is to be assumed that it should be composed of two identical segments. So what are those means? Here we should note that for the same end voltage, the magnitude of the total voltage across the series line inductance as Vx equals to 2Vx by 2, that is supposed to be hiked by the magnitude of the opposite voltage, comma OEC voltage, that means capacitor voltage, that should be developed across the series capacitor and which may result from the increase in the line current case. So here coming to the series compensation, we are providing this cumulative combination of capacitive reactance and normal reactance case that should be summing together, and these are excited by the source voltage Vs on the LHS side. These coefficients are supposed to be halved as x by 2 and xc by 2. So these coefficients are receiving end voltages reflected here, and based on that the phasor sequence is split into two cases. The splitting of the phasor sequences as a sending end voltage and a receiving end voltage. This is the magnitude of the final voltage that should be with reference to the consideration of the line. So here the sending end voltage is separated as minus jxc by 2i coefficient, and similarly the receiving end voltage is separated by minus jxc by 2i coefficient. So one of the two factors which will influence the system parameter. So as the curve is drawn in between power angle delta versus real and reactive power coefficients P and Q, then that curve may be going to hikes to the extent that will be 1 minus cos delta. So here the real power coefficient must be V square by x into 1 minus k sin delta case. Reactive power coefficient must be 2V square k by x into 1 minus k whole square into 1 minus cos delta. So here it influencing the parameters with one of the value k, that is 0.4, and k must be xc by k, and in some of the cases the k value may drops to the 0.2 and 0 cases. This drop in voltage are extended to the pi by 2 line with a maximum power consideration. So this should be achieved when this extent is 2p max. Then we are going to achieve the k value about 0.4. This should be happening under maximum case. And the reactive power coefficient under short circuited condition may be existing with 2V square k by x into 1 minus k whole square into 1 minus cos delta. So here effective transmission impedance with the series capacitive compensation is provided. That is, effective value of reactance is the total reactance x minus capacitive reactance x is going to be considered. When you treat this capacitive reactance with 1 minus k coefficient, then it should be effective reactance becomes 1 minus k into x, where here k is the degree of series compensation. That means k must be treated as xc by x, where xc is the capacitive reactance, k is the degree of series compensation, and x is the net reactance provided. Assuming that the voltages at sending end and receiving end must be equal to the nominal voltage V, then the current in the compensated line becomes 2V by 1 minus k into x sin delta by 2. where delta is the power angle derived. Where delta is the power angle derived under normal absorption conditions. So here real power transmitted becomes P equals to Vmi is equals to V square by 1 minus K into X sin delta. So reactive power supplied by the series capacitors may be treated with one of the coefficient called QC. Then it may be existing at an angle of XC, and that will be 2V square by 1 minus K whole square into X. This is the product of 1 minus cos delta coefficient. So here voltage stability is one of the major factor that will influence the whole reactive power compensation strategy. So series capacitive compensation can also be used to reduce the series reactive impedance. This is ready to minimize the receiving end voltage variation and the possibility of the voltage collapse also. Because of the stability of the voltage, the system response is smoother and the load can expected to run with 100% efficient conditions. So this should be minimizing the receiving end voltage variation and possibly with the collapse of the voltage. So we can suppose it to balance the system line voltages suitably. System line voltages. And coming to this, here we will treat simple radial system that will be considered with a feeder line reactance as X. So series compensating reactance as Xc and load impedance becomes Z. That means nose point at each plot is given for a specific compensation level that represents the corresponding voltage instability. So where the same radial system with a reactive shunt compensator supporting the end voltage is going to be treated. So that means here clearly it is mentioning that both shunt and series capacitive compensation can effectively increases the voltage stability limit. So shunt compensation supposed to be done it by supplying the reactive load. So the demand and regulating the terminal voltage can be suitably reached from the series capacitive compensation method, and which can achieve the suitability to the extent of the levels. So coming to here, one of the series compensation strategy, we are taking series combination of capacitor C and reactance coefficient X. This provides one of the series compensation strategy. So this must be connected across the supply and also treated under the load case. This must be treated under load and supply terminals case. So here impedance factor becomes equals to the R conditions. So when you treat this in per unit of voltage and power, then the curve representing as at 1 per unit case as Xc, that becomes 0, and when it is 0.5, Xc becomes 0.5x, and when it is 0.575x, then Xc becomes equivalent to this value. So here we will treat all these combinations from the point of 1, 2, 3, 4 like that. So these all will represent per unit values. So improvement of transient stability is considered. So that is the powerful capability of the series line compensation. This is ready to control the transmitted power that can be utilized much more effectively. So this is to increase the transient stability limit and also to provide the power oscillation damping. So when the oscillations are more into the line, then there may be absorptions in the system which may collapse entire line. So equal area criterion is the best method to investigate the capability of the ideal shunt compensation method. This is ready to improve the transient stability that should be used again here to assess the relative increase of the transient stability margin. So that should be attainable by series capacitive compensation method. So here this compensation strategy contains series combination of Xc by 2 case and X by 2 case. This series combination will result in to give one of the suitable case of X by 2 and Xc by 2. This combination achieving with the source voltage and receiving voltage case. That means the amount of voltage that should be sent from the sending end line is reaching to the receiving end line with reduction free of the all distortions in the output. So here we will consider a simple system with series compensated. So as for the shunt compensated system, it is for the convenience that we must assume for the series compensated case that pre-fault and post-fault systems are remain same in the case. Suppose the system with and without series capacitive compensation transmits the same power PM. That means we should assume that both the uncompensated and series compensated systems are subjected to the same fault for the same period of extent. This may goes to the high extent when it is considered with the series compensation strategy. So here dynamic behavior is one of the factor of whole the systems as it is prior to the fault of both of the transmitted power PM at an angles of delta 1 and delta S1. Then during the fault conditions, transmitted electrical power becomes zero while the mechanical input power to the generators remains constant. That is denoted with the PM. So therefore, sending end generator is ready to accelerate from the steady state angles delta 1 and delta S1 to delta 2. And it is also collaborated with the delta S2 respectively when the fault is supposed to be clearer. So accelerating energies are supposed to be represented by areas A1 and AS1. This is after the fault clearing the case. So transmitted electric power is going to exceed the mechanical input power and therefore sending end machine is ready to deaccelerate its locations. So based on that locus points considered, the system parameters are going to be happens. So however, it is the accumulated case of kinetic energy. This should be further increased until a balance between the accelerating and deaccelerating energies are represented by areas like A1, AS1 and A2, AS2 that is respectively reached at the maximum angular swings. So delta 3 and delta S3 are going to be reaching at the extent as a P to the delta case. So maximum power achieved during these conditions with the boundaries called A1 and A2. So these boundaries will have the maximum efficiencies with PM and P becomes V square by X sine delta. That is the total amount of power. The marginal power is going to be treated as A margin and here delta 1, delta 2, delta 3 up to critical value is going to be reached at the end of the line. This should be reached onto the line called power angle line delta. So from PM to P max, the extent of the line is reached at P equals to V square by X time delta case. So when it is 1/2 of the maximum power consideration with respect to the delta, this may be hikes to the extent with the PS equals to V square by X into 1 minus K sin delta, where K becomes 1 by 3 and here AS becomes the marginal value. This hike in the value with AS1 and AS2 goes to the maximal extent with 1/2 of the maximum power case consideration. So the areas which are existing in between P and delta curve and the constant PM line over the interval defined by the angles are delta 3 and delta critical and those are delta S3 and delta critical respectively. So transient margin stability also represented by a margin like AM and AS margin levels. So the comparison is clearly shows that substantial increase in the transient stability margin which will increases the series capacitive compensation of the line. That should be provided by partial cancellation of the series impedance. That is considered with the transmission line coefficient. So increase of transient stability margin that is proportional to the degree of series compensation. So therefore, theoretically, this increase becomes unlimited for an ideal reactive line as the compensation is supposed to be approached to the 100% of the level. So, however, in practical series capacitive compensation, it does not usually exceed 75% for a number of reasons, but it should include load balancing with parallel paths, high fault currents, and the possible difficulties of the power flow is going to be considered. So usually the compensation is limited to less than 30% due to subsynchronous concerns. That means power oscillation dampings are going to be treated. So controlled series compensation can be applied effectively. This is ready to damp the power oscillations. This is for power oscillation damping. It is necessary to vary the applied voltage of compensation levels. This is so as to counteract the accelerating and deaccelerating swings of the distributed machines. This will reach us to the maximum levels at the oscillation damping of the power system network. So here, that is when the rotationally oscillating generator is going to be accelerates, and delta increases means d delta by dt, that must be greater than 0. So electric power transmitted must be increases compensate for the excessive mechanical input power. So conversely, when the generator is deaccelerates and delta decreases, the electric power must be decreased to the balance to the insufficient mechanical input power case. So as k is maximum when d delta by dt greater than 0, and it is 0 when d delta by dt less than 0. So this is happened with the maximum value of k. So effective line impedance is minimum, or alternatively voltage across the actual line impedance also maximum. And consequently, electric power transmitted over the line is also treated as maximum under these conditions. So when the K value becomes 0, effective line impedance is maximum, or alternatively voltage across the actual line impedance also minimum. So power transmitted is supposed to be reflected as minimum case. So illustration of that work shows that K is controlled in a bang manner. Output of the series compensator is varied in between the minimum and maximum values. So indeed, this type of control is the most effective for damping of the large oscillations in case. So however, damping is relatively small power oscillations. So particularly with a relatively large series compensations of the line, continuous variation of K in a sympathy with the generator angle of the power, it may be to be better alternative for the whole system. So this is one of the undamped system lines. Here the undamped frequencies are represented here. This may result to the variations of the delta and delta naught cases. The whole power with respect to the P naught will be represented under undamped nature. This is one of the coefficient K with peaks generated at various intervals of time. This may represent the series compensation under undamped frequency ranges. So subsynchronous oscillation damping is considered here, one of the factor. This is sustained oscillation below the fundamental system frequency that can be caused by series capacitive compensation. So the phenomena referred to as subsynchronous resonance, which was observed early as 1937, but it is received serious attention only in the 90s after two turbine generator shaft failures occurred at the majority of the generating stations in the southern Nevada. So theoretical investigation shows that interaction between series capacitor transmission line oscillating at the natural resonant frequency and the mechanical system of turbine generator that is said to be torsional mechanical oscillation that can be results in a negative damping of the system. This may take place with consequent mutual reinforcement of the electrical and mechanical oscillations. This should have the continuous effect on the whole operating system. So here the phenomena of subsynchronous resonance can be briefly describing some of the key features. So a capacitor in series with the total circuit inductance. For example, if you consider a capacitor in series with the total circuit inductance L and C, so what happens means the transmission line, that is including the appropriate generator and the transformer leakage inductive nature, that forms a series resonant circuit. This is with the natural frequency F, where Xc is the reactance of the series capacitor and Xc is the total reactance of the line at the fundamental power system frequency F. That is Fe equals to 1 by 2 pi root Lc, that is F root Xc by X case. So since the degree of series compensation K equals to Xc by K, or it may be generated with X, this is usually in the 25 to 75% of the range. So electrical resonant frequency is less than the power frequency means Fe is a subharmonic frequency. That means if the electrical circuit is brought into the oscillation by some network disturbance, then the subharmonic component of the line current may result in a corresponding subharmonic field. That is in the machine which as it rotates backwards relative to the main field since T less than the F coefficient. which produces an alternating torque on the rotor at the different frequency of F minus Fe case. So if this difference of the frequency coincides with each other with one of the torsional resonance cases, the turbine generator is set to the mechanical torsional oscillations that is going to be excited, which in turn further excites the electrical resonance case. So this condition is defined as subsynchronous resonance. Of course, this process could also start in the reverse sense. That means a shock could start to a torsional oscillation, which under the condition of subsynchronous resonance, which should be reinforced by the response of the whole electrical network. So thus we can form the standard point of the angle correction circuit, which by comparison is supposed to be very fast, and the corrections are takes place in each half cycle. So output of the phase shifter is almost a steady state reference. That means although the control circuit performance are usually heavy, they dependent on the actual implementation. The second approach is the theoretical, more likely to provide faster response for those applications requiring such response. That means here we will consider a functional internal control scheme for the thyristor control switched capacitors that is based on the periodization of the capacitors voltage at zero crossing levels. That means the reference section is given here as VC reference. Error amplifier is connecting by one of the PI controller case. This will ready to balance the controllable phase shifter advance. That means that coupling is through the synchronous timing with PLL circuit, and this must be interconnected to the angle correction circuits as I and VC. This will ready to control over the getting the control signal by TCR. That means thyristor capacitor regulator. So here gate pulse generator is ready to connected to the circuit. This is connected by one of the mechanism of TCS, thyristor controlled switched capacitor, and this may generate a voltage VC, and it is flowing with the current I as inductor is connected into the series of the line. So these are some of the references whichever I have considered, and this gives the suitable information for the whole power system network under various controllers. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.